Today, I'm going to just talk, I'm going to kind of give a hodgepodge, as one does sometimes at the end. I'm going to make two kind of more comments on things that I omitted from the conversation yesterday because I was worried about time, but then I decided that now I have a little bit, so I'm going to just mention them a little bit. Then I'm going to maybe talk about just mention a few open problems. And then I'm going to switch and show you a different model for randomizing a PD. But I want to just be a little more explicit. So if we have the two-dimensional Navier-Stokes equation, let me just write it this way today for reasons that we can clear in a second, plus the bios of our kernel dot the gradient. So this is in vorticity form, just like every other day. It's Laplacian Q, and then I have some collection of k's in some z0 k of sigma k and some ek, just sigma k, let's say, d beta k t. So that looks like what I wrote yesterday, yeah? Now, again, so I talked about this yesterday. I'm just kind of saying a few things a little slower. If I now sum over all Fourier modes, so in Z2, and as usual, I had no mean flow, so I'm going to put a little zero there to say like the zero mode is gone, right? So there's no mean flow. And then I write this as QKT, yeah, e to the I kx. And I guess I'm putting x now that I've written that explicitly, which you should never do, because then you're in danger of making mistakes like this. I think I'll put it on the 2 pi course, yeah? So once I've written this in like this, I can now write it in Fourier, yeah? I can write this equation in Fourier. So I'm just writing this a little slower than I wrote it yesterday because I wanted to give you the impression yesterday. Now I'm going to give you. So this is minus k, you know, with that old joke that people always made and I always thought was really stupid, and now I'm going to make it, you know, like 2 pi is 1 and 2 is 1. Constants may be off, but I think this is, no, it's 2 pi. Is it 2 pi? I think it's, anyway, I might get it wrong. L plus j equals k, and then this gives the interaction of, let's just write it, CLJ, QL, QJ, plus, you know, plus this projection. So if I just for a second, for simplicity, let's take this vector to be some constant CK times e to the I k dot x, right? So I'm just going to force the k Fourier mode. And if I do that, then I need to write this. So then this would be kind of a, and you know what, I'm going to call this was my vector. I hate that, but I'm just going to do it for a second. So I can just call this sigma k and not confuse us. All right. And then I wrote WK because this really should be a complex Brownian motion. Okay. Which is each complex Brownian motion is just W K kind of hat T plus I W twiddle T, and then I guess divided by 1 over square root of 2. So those are Brownian motions. These are two real Brownian motions. You put them together like this and you get a complex value Brownian motion. And the C L J K L J okay. CLJ, that's fine, is equal to what? It's equal to the inner product of LJ perp. So there's maybe always a sign error right now when I'm doing this from memory, because I didn't get my coffee this morning. Did I get it right? That's shocking. The only reason it's right is I had 2 choices to make, which means I got them both wrong. I had a choice here and I had a choice here. And so I clearly got them both wrong. And so the sign is correct. It's like, I'm so glad I left. This is so painful. All right, so there we go. Okay, that's the thing written in Fourier space. And the reason I'm doing this is because I talked a little bit about the brackets, right? And the brackets spanning everything. And I just kind of wanted to show you why you might think in a system like this, you might have brackets spanning, okay? You know, and if you had some other equation, if you had your favorite reaction diffusion equation, what would you have? You'd have a Laplacian again, and then you'd have some convolution again, now with 3 terms and some coefficients in front, right? Right? So you can kind of imagine many of the polynomial nonlinearities that you love in dissipative PDEs, kind of, a lot of them look like this. Somebody will raise their hand and go, what about sine Gordon? Or, okay, yes, fine. But, you know. All right, and now I want to just do a little bit of a calculation, and I'm not going to do it. I mean, that's not true. I mean, I think the way, if you really want to think about this in a simple way, you should probably just stay in complex coordinates, but you could. So in the articles, what we've often done is we've switched to actually having a real basis, right? Right, because of the reality condition. You can put the signs here. You don't have 0, and then here. And then you can put the cosines here, and then the cosines here, okay? Over the whole lattice, yeah? And then you can rewrite this nonlinearity using that basis, and it'll just get uglier, okay? But I hope you'll believe me that the essence I'm about to show you is correct, and it gives you the idea, which is all I've been ever trying to give you, right? I've not been giving you like what you could go home and do exactly. You have to go home and do it yourself, but I'm just highlighting to you that I'm going to pretend for a second these things are real instead of being complex, just because I think it makes the point more clearly. And if I have to deal with the complex one, it becomes messy. Okay, and there's a little twist thing, and it just becomes a pain, and I can't do that extemporaneously. Sam's just pointing out to me that you can actually do this all complex, and in some ways we should all switch to doing it that way. I agree with you. I know. I saw your eyes. He's like, no. Okay, so look, what's happening here? So I need to remember. This is my bilinear form. Remember what happened last time? I started taking commutators with the nonlinearity, right? So let's just remember, let's just remind ourselves. So what did I have? I had some xk's, which were sigma k dot grad, right? And now this gradient is in this whole set of this basis, this infinite basis, right, of Fourier coefficients, yeah? Right, so so what direction is this? This is the derivative, so it's dotted with this. So this just becomes this number sigma k times the ek coefficient, if I'm just pretending everything is real, yeah? Because that's the direction I have noise, right? And so now let's just call this. So first of all, if this thing is linear and it's going to go away, it's only in the directions I'm forcing anyway, it's not coupling any modes, so I can just ignore it, okay? So let's call this B, K, Q, Q, yeah? What I'm going to claim is if I do this, remember I could take this, and then I could do an XK here, an XL here, right? And then I could do an XJ here, right? You remember how this worked? I took first the commutator with one of the noise directions, and I got something. And then the next layer, I was allowed to take things that I got in the previous layer, again with the directions that I had noise, right? And then I kept going, right? What happens if I do this 3 times in this problem? That's not a lot to answer this question. Yes, but Kyle answered it, so I'll take that answer, 0. Okay, right, you get 0. Why? Because you took 3 derivatives of a quadratic polynomial. We all know that 3 derivatives of a quadratic polynomial always give 0, right? We can all agree on that. So in some sense, this is the only thing I need to think about, various versions of this. Now I could, yeah, that's right. That's all I need to really think about. And now what happens when I do this? Basically, when I do the XL, I get only the terms that survive where there was a QL here, right? And so I basically get, what do I end up getting on this first one? I get something that looks kind of like this. I get something, I have kind of the e-kth, I have the e-kth direction, and then I'm summing over J, and I have CLJ, right? And what is J equal to? J, remember, J plus L equaled K. So that means that J has to equal K minus L, right? So I can just go ahead and put this as, so sum over, right, no, so I'm summing over K, and now this is K minus L, right? And then I have Q K minus L. Sum over sum, and this K is inside. There we go. So that's kind of the vector field that I get after this first bracket, right? This first bracket, just to there, yeah? And now what's going to happen if I take another bracket of this with some other direction, xj? What am I going to get? I'm only going to get the time when K minus L equals J. And so what I get is I'm only going to get the EK, but now where K equals J plus L, right? Yeah. And then I have CLJ. All right. Now there's a lie here because it's not all real. And so it's slightly more complicated. But it's a noble lie that I'm telling you because this is the essence of the idea. Yeah. Like, in fact, the way that this happened was I went home one night and checked this. And then I spent a lot longer just figuring out how to organize it in the complex case so that it was sure it would work, but so that I can actually write in a paper. And some people still tell me I didn't quite succeed. Mark, say that out loud on tape. It was a nice thing I was about to say to someone. Okay. All right. All right. So then when I take this, I get this. Yeah, everyone agree? So what's the only thing I need to worry about? I'm only allowed to use, the problem is this thing could be 0, right? So I get a new direction, right? So you can think about this on this lattice, right? You can think about it on this lattice. So if I have this one and this one forced, what? Ah, thank you. Okay. So she already told me, she had a very good. Okay. So here's my L and my J. What this means is that now I can also get what? I can get that one, right? Next, yeah? And then I can get, it actually turns out you can also get the negatives, right? So why do I have the minus? If this is a real vector, field, right, reality condition says that if the kth mode is being forced, if I want to force real forcing, then the minus kth mode has to also be forced, yeah? Because that's just what it means to be real for a Fourier series, right? So that means I can also get this one, right? Because I could just apply minus this vector to get that, yeah? Because I also necessarily have to have that one. Yeah, and I also necessarily have to have that one, right? Oh, sorry, I guess I meant that one. So I did that wrong. Okay. But the point is you can start moving through the whole space, yeah? You can start moving through the whole space. Yeah. And so it turns out you can prove this theorem. This is a theorem that you can ask yourself, well, what about the additive lattice? Well, the additive, like what I would generate as a group from the ones I initially forced, where I just add the indexes. So you can say, you can start with some forcing, some set of forcing here, this set of forcing Z0. And as long as that initial set of forcing generates all of the Fourier, all the indices, and you had some way to get going. So kind of the only obstruction is that all the modes you force, what happened if all the modes you forced had this coefficient 0 when you had them interact? Like think about 0, 1 and 1, 0. If this is J and this is L, then CLJ is equal to 0. Because these have the same length. So this term is 0. So as long as you have some way to get started, then the statement about the additive group of just adding the coefficient indices is actually enough. You can prove that in this case is enough to generate all the directions in the algebra. Okay, so you have to do things like that. And when in Sam's talk, he talked about the extra complication that Alex, Jacob, and Sam had to deal with was that they were also interested in the lyapunov exponent. And so they were worried about this extra set of directions in the tangent bundle. And that gets much harder. That's much more degenerate. This is already pretty degenerate, right? I'm only using a finite number of forcing. So for instance, these two right here, if I only force them, that's enough to do everything. Because I can get started. And clearly, if I can move up and down and left and right, I can go everywhere. Yeah?
So sorry, just to make sure I understand what you're saying. You need a lattice basis to get where you need to go. But in addition, you need that lattice basis to have at least one interacting pair?
Yes, at least one interacting pair. That's enough. It's just a, it's the kind of thing you're like, oh, there's clearly an obstruction.
Yeah.
Right? That's clearly the case where you can't win if you have none that interact. It turns out that's the only obstruction. It's a half a page to a page.
That's surprising that there's only one.
Yeah, we were happy. It wasn't the first thing we tried to put, right? This was like paper 3 in this series. And each time we did something a little smarter. Yes.
So I think, this computation shows that given vector direction that can be written some of J Pascal or J Pascal, J and L are in the one direction.
Yes.
Then you hit. But
yeah, what you're saying is that, I should have said, you don't actually have to exactly force in those directions. You just have to have directions that span these for you, coefficients. That's good enough. I didn't put that wrinkle in because I just didn't want to confuse the conversation.
Did anybody, you or anybody else, ever try to compute all possible combinations? Like this shows that you get a non-zero contribution. You do span.
Yeah.
But is there some kind of mass, like the amplitude by which you hit that node and then consider all possible combinations?
Yeah. So I wrote a Maple script to do that once. Back before I probably knew it was enough about and it crashed. Now probably with things like Mattingly and things like that, maybe one could do this in a better way with modern Globner basis techniques, but I don't know. Have you ever done that? I've thought about doing it. Yeah, you can imagine a whole tree of things that take you in different places.
It's conceivable that those trees would carry
more
mass.
Oh yeah, very much so. Yeah, I'll just restate his comment. His question was, I found a sufficient way to reach from one place to every place, but you actually pay a cost. The more brackets you take, if you know a little bit about the theory of hyperellipticity, there's a Carathéodory distance that tells you kind of how things decay in time as you get. The more brackets you need, the weaker the noise gets there. And so what Vlad is asking, which is something I've been very interested in, it comes to one of the open questions, which I'll just go ahead and state now, which is what I was going to come to this, right? So solve the asymptotics of one of these iterative systems in a way that you can kind of tell what mass is attributed to a certain mode when you're only forcing a few of them, right? Relatively to the other, and solve it out to infinity. So you don't even need viscosity. I don't need that here because I have viscosity. Let me just say what the message from last time. I have viscosity, and so I only need to get to a finite number of them. So it's kind of like saying, people don't usually ask like, how elliptic is your system? They just say, is your system elliptic? Because the minute you have it, you get all the other stuff for free. If I wanted to do something in infinite dimensions where I actually understood the scaling limit or some kind of, pumping through a cascade, for instance, I might really want to understand the asymptotics. And I think it's a super interesting question. And I don't think there's a few solvable examples, but they haven't been understood this way. It's on my to-do list, but there's lots of room for lots of smart ideas. So don't let that somebody's thinking about it make you scared.
Can I mention too that so I think there's like if you only work in the first order brackets and you use the drift more,
Yeah.
it's a huge algebraic mess, but you're able to span a lot more.
Yeah.
And you get much better regularity because of the way the Ormonder scaling works.
Yeah.
But it's extremely algebraically disgusting.
You would think that people's more good at
Maybe.
You'd think, yeah. It's like a.
But I mean, in a way, that's one of the things that's missing now. That's what we need. Is we need more injection of the actual transport properties. Yeah. Okay. So put that as open question. Does that sound good, Vlad? Groovy, thanks. All right, so how much time do I have left? So let's see, I have maybe, let's see, that took longer than I thought. All right, so let me just make a few more comments. So I mentioned last time, so let me just tell you a general theorem. So I said this last time. I said, if you replace this equation here, well, now you replace this with some u of t, where u of t is some nice continuous function, u of tk. Now you get some control dynamical system. And so you can use control theory to move this around. And it's a theorem you can prove for this one, is that you can actually, if you give me a point in Fourier's, a set of coefficients, a set of coefficients, I can steer it so that I agree with that set of coefficients up to any order, like the first 100 coefficients, the first 5,000 coefficients, the first 2 million coefficients, okay? Actually enough then to prove, it's not enough, you need that map has some differentiability properties, but this polynomial PDE is Fouché differentiable in these things as much as you want, okay? And you just have to make sure it doesn't blow up, which because of our old friend Laplacian, you're fine. And so you can steer from one point in Fourier space, some set of coefficients, to another, the projection of any other point. So you can make it match up arbitrarily, okay? And then the only thing you need to know, to any finite order, you can't match it infinitely. And then all you need to know is that trajectory, if you linearize about that trajectory, Jacobian is non-degenerate. And that Jacobian is exactly, that Jacobian transpose, adjoint itself is exactly the Maillard matrix I introduced last time. All right, and so now people get really worried about, like, how do you know that if I build this really esoteric control that you can connect here to here? Here's a trick, which I'll tell you. And since you're at a random, it's beautiful marrying of the stochastic stuff and the deterministic stuff. So it's perfect for this conference. Here's the trick. Remember what the Maillard matrix looked like. Linearization of the directions you were forcing tested against some direction squared ds, right? This was m of t c, yeah? If this becomes positive definite, extending it longer in time doesn't do anything, right? Right? Because you can split this integral up into two parts, right? So what you can do first is you can take the first part of your control to actually be the Brownian motions. As the calculus, you can show that that's almost surely non-degenerate. So you can pick any Brownian motion you want and stick it on the front, and it moves you somewhere. And now you can use whatever horrible controls you want to move from there to wherever you want it to go. And because the first part made it non-degenerate, you don't care about the second part making it non-degenerate. It doesn't matter. It won't collapse it. Once it becomes non-degenerate, it won't stop it. Okay. So that's a cute trick that lets you then decide that actually, not only can you get to every point like that in projecting down, but you actually carry density with you. And so you know that every point is in the support. It's a point of positive density. Okay. So now you have a density with respect to a big measure, which is positive. All right.
Wait, so like you're saying that the kind of like the higher mode you get, like the weaker the forcing will get if you're only forcing like a few of the modes, and then we're only able to like steer finitely any of them. We can steer them to, we can only specify that what a finite number of them to agree. Okay. The control theory is not strong enough to do the whole system. Yeah. You obviously can't steer everywhere.
It's false. You can't.
Right. I was going to say it in a different way, David. Yeah. There's some manifold which you can steer exactly to. Specifying that manifold submerged in L2 is very hard. But that's the same thing as David just said. I just don't want to say I can't, because you can actually steer to the places you can go. You just don't know what they are ahead of time. Yeah. All right, very good. All right, so great. So why don't I just state a few other open questions? So the first question I just talked about, understand, got that all wrong. Understand limit of brackets and shortest / cheapest between 2 points. Like if you want to go from, if you want to generate motion in this direction, between two to a direction and at a point. Okay, so you want to say, I want to get over to this point, I want to have action in this direction. What's the cheapest way to do that? How should I wiggle, and there's a distance you can put on, like if I need this many brackets or if I'm going to use this brackets to do it, there's a Theodore distance which talks about, there's a sense of cheapest. Okay. All right. So that's one thing. Another question. So remember, I mentioned 2 things, right? I mentioned that for Navier-Stokes with a little bit of hyperviscosity, I could prove that the transition densities, if right, so in setting, I should say in setting. So this is kind of in a way you can almost say this is like understand true hyperellipticity infinite dimensions. In this setting, this is kind of understand ellipticity a bit better. In this setting where sigma k is equal to 1 over k to the p, so think p bigger than, I don't know, 2 or something for Navier-Stokes. If maybe I need 4, make it 100. So if add a little bit of hyperviscosity, I said I can prove, so with Laplacian going to Laplacian 1 plus epsilon, understood as minus, then you can prove that PT U dot, remember, was absolutely continuous with respect to the Gaussian. When epsilon equals 0, we could still prove that PT U dot was equivalent to PT U tilde dot and equivalent to the invariant measure. But can you tell me something about that measure? Can you show that there's some Gauss, something, right? And then the same thing is true for Burgers. So for KPZ, for all the way up to KPZ, right? That's when this P becomes in this notation -1. For anything less than that, I can show is absolutely continuous with respect to the Gaussian. But at P equals 1, I can't. Unless you force exactly with the right white noise. And the same is true for Navier-Stokes. If you force exactly with the right white noise, you know this absolutely continuous with respect to Gaussian. But I claim that's just a statement about geometry. That's because the drift is exactly tangent to the level sets of the invariant of the Gaussian of the linear density at every point. And so it's a geometry statement. What else do I have written down here? I mean, of course, understand the limit as nu goes to 0 of any of the kind of ergodicity that I showed you here. We don't understand the limit is vanishing viscosity of any of these controls. We can show that if you have a viscosity and you approach that viscosity from above or below, that everything converges. The invariant measures converge, everything is good, but we can't go all the way to 0. Okay, so we have the invariant measure as continuous in all the data, the forcing strengths, where you force, things like that. We can't show that it's, and the viscosity as long as you stay away from 0. So how much time do I have left? 30 minutes?
15 minutes.
15?
Actually, more than 15, 18.
18. Approximately 18. No? She didn't laugh. It's not here. Must say, ooh. Non, mais c'est pas assez illuminé. Au revoir, c'est pas là. Oh, I see. Ah, je comprends. Merci. Yeah, no, so it's perfect. Great. Thank you. Now I understand. Sorry about that. All right. So am I there? Got it. Share screen. So now I'm just going to take a second and show you a different model of how to inject randomness. Why? Because I think I want to encourage people to remember why we were putting randomness in there and not marry the problem too much, not marry a specific problem formulation, right? Let's see. Oops, sorry. Try that again. Oh no, where'd it go? It's closed. How'd that happen? Centrical Mar. I know. It's like I feel like you must have taken over my machine. All right. So let me just kind of go away. and present. Okay, great. So I'm going to show you a little different model. So a lot of this I'm going to fly by because you've been listening to me talk about this a lot. All right. So there we go. There's the equations again. Yeah. Let me just go. So we just talked about the stochastically forced one over here. Let's see if this pen works. Yeah, it does. And look familiar. So maybe apparently I don't have the pies. I think I may have made a mistake. Huh?
No pies.
No pies. Okay, yeah. I was on a 0-1 box in the paper I was thinking of. All right, so I have energy and entropy here, right? Which are just the, so if I'm in the vorticity formulation, the entropy is just the L2 norm of the equation, the sum of the coefficients, and the energy is the coefficients divided by this, okay?
A way to close that.
I don't know how to do that. Ah, I see. Got it. 3 computers, 4 input devices. All right. So, of course, deterministic Euler has a ton of conserved quantities, right? Entropy, energy, any function of them. In fact, Kelvin circulation, any Croce curve you draw, you have nice. So let me just skip ahead here. Okay, this is the spanning thing I just talked about. Sorry, I should have made a dedicated deck, but I wasn't sure how much. Okay, right. This is, darn it. There we go. All right. So what I want to think about with this different model is I want to split up 2 ideas that are going on in this random conversation. I want to separate what's putting the energy into the system and what's keeping the dynamics generic. I want to separate the roles of those 2 things. There's lots of ways I could have done it. I could have even done it still with just stochastic forcing, except for the third goal, which is that I want really simple dynamical systems that are coupled together that I can maybe think about. All right, I want to let my geometry and my dynamicists come back into play. All right. So here's a movie of one of the systems I'm about to describe to you. I don't know why. Somewhere along the way, I got the idea that I should show you the movies first to convince you should pay attention to what I'm about to tell you. So here we have some vortices spinning. Unfortunately, it's true that it looks better on my iPad than up here because Zoom subsamples the videos so that it can send it. And this is the energy and the entropy. Okay, and the next picture actually shows it to you in log coordinates, the same picture. Thermalize in a second. It's going to kind of start to drop down. At least the entropy will thermalize. It starts to get flat, which is not surprising. This is a divergence-free vector field on this space. So we kind of expect the Lebesgue to be invariant, in fact, without any kind of energy flux boundary conditions. Here's a really great one. 2 interacting vortex pairs. Okay. All right. So let's skip this again. Okay, so now what I'm going to tell you about is this is the model that I'm going to use. So I'm going to take, so what's also one of the points is this is going to be a model of randomness in Euler, not a model of randomness in Navier-Stokes. Right, so it's like, how much do I have left?
13.
13, wonderful, my lucky number. Okay. All right, so what I'm going to do is I'm going to look at this vector field here for Euler, which is the one I just wrote down there, yeah? And I'm going to write it as each of these is like its own little vector field, yeah? And then I'm going to perform operator splitting. So I'm going to evolve according to each of these vector fields separately, one after another. Don't do this as a numerical method. It's a really bad idea as a numerical method. I'm not claiming this is a numerical method. This I would suggest for this, but it's going to be a slightly different way of introducing randomness in kind of an Eulerian way. I mean, Eulerian way, yeah. So what I want to do, and maybe I should be doing it Lagrangianly, that's a conversation we can have. So here's my little vector fields. So my vector fields are these little triplets. And now what am I going to do, of course, is instead of doing operator splitting where I run them each for the same amount of time, I'm going to run them each for a random amount of time. Okay, so this is some work I'm doing with.
So each little vector field has a CFL timescale, right?
Yeah.
So your time is random but unweighted by the CFL.
Yeah, I thought about doing both, but for the moment, I'm not weighting it by the CFL timescale. I agree that would be also interesting, but there's some analytic advantages to not doing that. And I should also say at the moment, I'm only talking about Gluckner approximations. I think we can prove convergence now, but on finite times. Okay.
So wait, Vlad, are you saying that the high frequency ones are moving faster, basically? Yeah.
I'm moving faster here. IID And this is just, if I want to do Navier-Stokes, I just put in a dissipative and a forcing term. And now I have some Markov semigroup. And then I have this, the original deterministic semigroup of Euler. And so there's a lot of work in this right now, but let me just kind of, since I just want to skip ahead. So, okay, I could also talk about Lorentz. I'm not going to talk about it right now. Let's just stick with Navier-Stokes. So what we can prove, the first thing we can prove is just a sanity check, is if you fix a finite time and you take enough steps to get there, m steps at step size h, so I'm taking exponential random variables with mean h, okay? Then these two things converge in some norm. This is C0 to C2 norm, okay? I didn't really care about how good this norm was. All I wanted to show is these converge. And Lorentz 96. So let me just show you what happens in Navier-Stokes. So in fact, we don't do that. We actually split it into the real versions of all those vector fields. So you actually, instead of just getting those complex ones, we get this whole set of real interaction between J, L, K. So in the real part and the complex part, and we could actually randomize how we do this, but this is good enough for this talk. And what's interesting about them is that each of these little systems conserves energy and entropy. Each of them conserves energy and entropy. So this whole splitting scheme conserves energy and entropy, right? And so what they do is they're just this dynamics of this little green curve, because they're in 3 dimensions. They have 2 conserved quantities. And so they're living just on a curve on a football. The intersection of a sphere and an ellipsoid. Lots of other splittings you can do. I'm thinking about some others. Sam and I are having some really interesting conversations. All right, so we have a theorem for Hausdorff. I'll just go ahead and state that. So for Lorentz 96, which we've had some people talk a little bit about here, which is just a simple model come up with by Lorentz, we can prove that as long as you don't start at one of the fixed points of the right-hand side of the equation, then if you think about Lebesgue, these are each invariant measures. So somebody asked me, you keep saying everything's unique and ergodic. Can you give me an example where it's not uniquely ergodic? It's a random system. Here's one. If you start on any of these fixed points, you're stuck there forever. The noise never gets you off. That's how this randomness enters. So, but we can prove that there's a unique invariant measure which is absolutely continuous with respect to Hausdorff measure on the sphere for Lorentz. And if you go to the Euler equation split, there's a unique Hausdorff measure which is absolutely continuous. Actually, it is Hausdorff measure. The Hausdorff measure is the invariant measure of the system. And it's slightly more complicated. You have to exclude a whole set of funny points, which, not surprisingly, I really would like to find a better way to do this, but like I said, it took me 3 times to get it right last time, and this is just time 1. You'll notice there's some complicated lattice operations that move you around, which are very reminiscent of before, but now they're on the initial data. They're not on the forcing, they're on the initial data. And if you have initial data with enough non-zero components, you're guaranteed to enter into the vault. But there are actually submanifolds that are invariant, that this randomization never moves you off. But they are all of Lebesgue 0 in the bigger set. Elements of ergodicity. All right. So does this picture look familiar to anyone here? The proof is the same proof. We actually showed that by wiggling the times a little, the map from the times into the space is actually surjective. And that the equivalent of the Maillard matrix, which is written right here, the thing that's inverted here, is actually almost surely invertible. The reason I want to show you this to you is also to point out that the ideas I've been selling you, they're broad. Yes, Professor Herzog.
So the only randomness is in the times.
Yes, sir.
Okay.
All right. Okay. So, and in fact, we can actually get a nice. I mean, it's actually we get it from the co-area formula, right? Oh, that's the theorem. Lorentz. Oh, one second. What was that? What did that say? Did anyone read that? Oh, right. If you add, let me go to Navier-Stokes. If you add forcing now, so if you add a dissipation matrix, which it can't yet be partial dissipation, but I think it's completely doable, and you add a body forcing, as long as the dissipation matrix applied to the body forcing deterministic is not on one of these bad sets of initial data, then you can actually prove that the whole system is uniquely ergodic, has a spectral gap, converges exponentially to equilibrium. Lastly, thanks to how much? 3 minutes? My chronometers.
5.
5. Yeah. So since Sam already did a nice introduction to lyapunov exponents, I don't have to talk about it too much except to say that, also Oscillatic's multiplicative ergodic theorem talks about the flag, these lyapunov exponents that are almost surely deterministic. And since I am really in Euler, so I'm going to prove this for this approximation of Euler. Since it preserves Lebesgue measure in its divergence tree, this thing, it could actually, or I should say Hausdorff measure, it could actually be that every one of the lyapunov exponents is 0. And we can prove now that this is still being written down, but it's right now. The stochastic dynamical system almost surely has positively exponent if you start the system in the Hausdorff measure on this surface. So if you start from that invariant measure, then you have positive lyapunov exponent almost surely. And right, I mean, this is certainly Jacob and their work is really wonderful, and this one is just going. So while they were thinking about how can we get something out of taking the viscosity to 0, I was like, I'm not going to think about that. I'm going to just go straight to Euler. And so I tried to make up a model on Euler that I could do it before. So the proof of the positive lyapunov exponents. I don't think you showed anything, did you? Did you tell how the proof went? I forgot.
Our proof is definitely different.
No.
There's some rigidity.
Right. Yeah. I know it's different. Yeah, but I just try to remember if you even told them anything. I don't think you did. So, so what?
I did.
You did? Okay, I couldn't remember. I couldn't remember if you gave the elements of the proof. That's what I couldn't remember. That's what I couldn't remember. I've heard you talk too many times. They all flow together. That's the thing. So, so we basically use some most closely to some ideas of Baxendale. And we kind of rule out some statements. If they were 0, there would be rigidity, and so it leads to a contradiction. Since you already heard it from Sam, I'm not going to go through it very much. But it's different, but it's in the spirit, which builds kind of on first. And here's maybe the one thing that I will say for this PD interested argument thing is that this dynamics that we've chosen, these little 3-dimensional dynamical loops, they're nice because they actually have shearing in them. And that's the most important thing to preserve in this model. And so every one of these little things have shear. And so the whole reason that we prove growth, the way we prove growth is by doing loops from point to point and then watching the vector in the tangent space. And because of the shearing, we get a simple matrix like this. That's the dynamics we have. And it creates shearing. And so if you go around once, you get a certain amount of growth. You go around twice, you get more growth. And so we show that it can't satisfy the rigidity. All right. Now, oh my God, what's this? Go away. All right. So maybe the last thing, that was the rest of the proof, but I don't think we need to see it right now. So I want to just say one last thing before I go to show you movies to close out and answer questions while I'm showing you movies. Is I'm going to show this to you because I was horrified. I read a lot, like you go to Google, like we all do research nowadays. Quantitative splitting estimates, quantitative Baker-Campbell-Hasdorff estimates. Okay. And then I was reading some stuff in a completely different field for a different reason. And they did something like this. And it's like, you know what it is once again? Duhamel. So if you take the splitting, which is this product here, right? And you differentiate it, you put a scaling parameter in front of all the K's. And you differentiate, you get this V drops down when you differentiate, yeah? And then you commute it all the way out. And if you commute it all the way out, you actually get the original vector field you wanted, plus some error term. And then you use Duhamel to say like the randomized one minus the original one is just this thing on the right-hand side. And you show that these things have the right order. And you prove it that way. Yeah. I'm sorry, it's like one of those things that I tried for so long to like I'm not going to reinvent the wheel. Everyone must know how to do this. I'm just going to find the right paper. Strickhardt kind of actually has something like this, I should say. But it was only in retrospect that I understood that. The measures look like. Let's watch the movies. So here's some longer runs. So they definitely thermalize like I claimed. Right? There's a little bit of boundary effects and some things we're still understanding, but and maybe what's more interesting, let me go to this one. So now I'm going to force it. So I'm going to put large scale forcings and I'm going to put dissipation just at the finest scales. And I'm going to put 2 different viscosities. This one, you're going to see a nice little maybe a cascade setup. Oh, maybe this one, actually, I might say this one. This one doesn't have enough. There's too much back scattering, so you get thermalization. This one seems to set up some nice slope. Yeah, maybe, yeah. Here's one where I put mesoscopic forcing. So I force in the middle and I do this. Same kind of thing, just to kind of show you what it looks like. Well, what's nice about this is this forcing is deterministic, right? It's a little jiggled, but it's basically, the structure of it's deterministic. So it's not like changing which modes have got more forcing. So that also gives some hope of some interesting structure. So I'll show this last one just because I love these pair of vortices interacting. So I should say this was done by a graduate student at Duke, who's really Nikhil, who did a really great job in numerics. And this is joint work with a graduate student, Omar, and a former postdoc of mine, Andrea, who's now left for Pisa. We're done. I think I'll just leave these running, and I'm happy to take any questions about anything I've talked about. Or things I didn't talk about.
Any questions? Additional questions, please?
So this might just be a misunderstanding of the model, but I just don't have good intuition for it. Oh,
So in this operator splitting, right, where
Yeah.
you're individually evolving them for random times,
Yeah.
each of those are just deterministic Euler modifying just those,
The
right?
only thing that changes is how long I run each of them.
Okay. What is your intuition as to like the mechanism that produces Strong-Feller in this situation? Because I would sort of anticipate if you're just randomly switching between some shear terms, that would be a weak Feller, not a Strong-Feller type of flow.
What's weak Feller?
So weak Feller is a maps bounded continuous functions to bounded continuous
Oh,
strong.
weak Feller. Oh,
Yeah,
that.
yeah, yeah.
Oh, just Feller.
Yeah, sorry.
Feller.
Sure.
Yeah, okay. Yeah. I mean,
I understand.
these
Yeah,
names,
yeah.
by the way, should have nothing to do with each other except that the same really, really smart man thought about them. Because the first one should be called well-posedness, Feller, and the second one should be called smoothing. So the first one is well-posed. I mean, it's well-posed. So it's because I can prove that it is strong Feller, because I can actually prove, I didn't tell you that, we prove it's strong Feller.
No, but my question is basically, what's your intuition? As to
There's lots of, you said intuition, so I'm going to give you the answer with intuition. You moved forward and now you randomized it a little bit. So there was a little bit of wiggle there. And so there's a little density in space, like you could have ended up here or there. And now another flow comes along and it moves it like that. So this chunk now gets spread out. And now there's a little patch of density here because the dynamics have a little bit of transversality. And then there's another one that comes and it spreads out. Now you have a little 3-cut volume. And if enough things happen, you get full volume.
Tell us more
Love.
the thermalization. The thermalization you showed on the pictures, those are for Galerkin, right?
Yeah.
You would not expect them for
No,
the
I would
whole.
not. Well, okay, so we have to be careful. But I would not expect them for Euler. How I prepared my initial data, right? I mean, I can imagine really smooth Euler data that might thermalize. I mean, somewhat. No, I guess I don't. Maybe decaying. No, I guess I don't. I mean, yeah, no, I don't. I mean, you need to, or you kind of expect there to be a never-ending front moving out. No?
Questions?
This is kind of the starting point to like start to try to.
Let's send Jonathan again for all 5 lectures.
I'll just say that I have to leave soon after this because I have an airplane to catch, but I really thought this was a great conference, modulo some of the talks. Mine. But I thought like it was really nice to be back in person and just how also what Scott says things. And thank you to the organizers, really. And I really felt it was a really interesting energy at this conference where we all were really talking a lot to each other and lots of interesting questions and lots of interesting ideas back and forth. So I really applaud the organizers for figuring out how to make that happen.